Basically, this is about hardware design and development. Basically, a little bit about our company, MindMajix. Um, Basically, MindMajix is a leading global online training platform holding 8+ years of experience in all IT courses. We basically offer courses in a wide range of categories like project management, big data, business intelligence and analytics, server administration, you name it, DevOps, AI, machine learning. Of course, hardware design is also one of the courses. That's basically what we're talking about today. And our instructors are all basically industry experts. They have earlier worked in industries as product development or product engineering groups and all that. With everyone is more than 10+ years experience, domain expertise. We focus on the quality of the training and all that. We have trained so far more than 400,000 students around the globe. We train uh, uh, participants from US, UK, Germany, you name it, Singapore, India, of course, and any part of the world for that matter. And there are a lot of participants from other countries also that participate in these trainings. We often update our course content quarterly on a regular basis so that we teach the latest and greatest, and basically um, that way we stay in tune with the changing technologies basically. And yes, we boast of delivering best in the class training for both individuals and students, and it is basically a trainer trained sessions where basically there is interactive understanding and interactive responses back and forth that basically enables the participants to learn much more faster. About this hardware design development certification training, basically this course gives an in-depth knowledge of electronic fundamentals, right, and focuses on microcontroller based design. And basically we discuss several things that are involved, such as EMI, EMC protection, CAD systems, etc. And basically focus on design that suits basically an industrial application. You know, the training includes deep learning of electronic circuit design, uh, right, and PCB design. This course also covers various real-time projects. Basically, we discuss about different projects, and then throughout the course, the focus is on basically developing a hardware on the participants' own in development, raise the capability of the participants to the caliber of basically developing a real-time hardware board. Right now, this webinar is basically focuses as basically talks on certain topics here. It's a wide range of topics that are basically set forth for this. It's one is the introduction to hardware design and development process, analog and digital design world, and basically talks about talk about active elements, passive elements. Just touching the basics, the of the voltage source, current source, and the discrete components like amplifiers, op amps, logic gates, flip-flops, counters, and then a little bit about power supply design, and then listing out the microcontrollers, the peripherals, the communication models and communication mechanisms, so to say, that are involved, and also understand what is a PCB, what's it like, and what kind of PCB types are there, right? So basically, we're covering the subject at different pockets of the subject. So to give a grasp of what to expect from the course. It's there are so many things that are basically covered, including basic design flow of hardware development and career and job rising opportunities for hardware developers and all that. So it touches only very introductory level each of these topics, The course specifically goes in depth and talks about each of them. Each element topic here may be discussed in 1 or 2 sessions, or even more number of sessions, depending on peripherals and stuff like that. So just sit back and relax, and enjoy the webinar. And if you have any questions, please hold on to the Q&A session. Then all the questions will be answered. And it's basically only going to talk about an introductory level at this webinar, because there are so many topics that are to be covered in a 1 hour's time. So don't worry if you don't follow some of them. Some of the jargon is not followed. For those that would participate in the in-depth sessions, that would basically be covered and answered also. Now, typically, let's look at a hardware development process. A hardware development process really is a stage-wise process. Basically, the first thing that the team, the hardware development team, would do is basically a system analysis. A system analysis is understanding of what kind of hardware boxes need to be created, and how are these boxes, how many of these boxes are going to be there, where are they going to be located, how are they going to be networked, are they going to be networked, and what is the functional capability of each one of these boxes, type of the boxes and all. So thorough complete system analysis in terms of the communication mechanisms involved, and the user interfaces that may be involved, and the automation that need to be taken care, the functions of each of these hardware boxes, and the software that need to be put in. These are all basically done at the system analysis. The output of the system analysis, of course, also focuses on the software development and all that. But then, as part of the system analysis, the one of the outputs that comes out is basically HRD, a hardware requirement document. So that would basically tell what the hardware that you are building, right? Which is maybe only a part of the entire system. The system may include servers and storage and whatnot, many things if you're building an IoT and stuff. So the HRT basically is an input to the design analysis. The design analysis basically process essentially creates hardware design document that tells what the hardware is, the block diagrams that are involved in the hardware, what is the memory capability that the hardware need to have, what are the peripherals that the hardware need to have, and their capabilities, the speeds of the peripherals, etc. Those are all will be captured in the hardware design document. Right? Once the hardware design document is done, we know really what the hardware is going to be like, what it has, what kind of components it may have. And so the next step is really the involved design, basically called schematic capture. That really focuses on the interfaces between the chips, selecting the components, and the interfaces between the components, and whether the interfaces are compatible, and they take care of all the parameters of the interfaces, and the signal levels and whatnot. Every aspect of the electronic design is basically carried on in the schematic capture. So the output of the schematic capture is basically schematics and the BOI. And of course, there may be other secondary things called netlists and other. But the netlist is basically a logical description of the circuit essentially, right? So the schematic capture is the next process. Once the schematic process is over, it's given up to layout engineers, and the layout engineers basically create the layout, and then they create the Gerber, right? The Gerber is given onto the fabrication, and the fabrication essentially creates the PCB and then populate the PCB. The fabrication team basically develops a PCB of the hardware. One or two or multiple PCBs for the hardware that is under the discussion. And then the next step is the testing of it, both testing of the hardware and also testing of the hardware with software put onto it, proper software or the drivers or the diagnostics, and all those things are involved in the testing. The testing essentially will basically generate engineering test plans, test results, and of course certification that it complies with whatever certification that the testing focus. There may be many kind of testing that are involved. We will not go in depth into that discussion in this presentation. But this is what the hardware process flow is, a stage-wise process flow. Once testing is done and you verify that all the hardware interfaces and hardware functionality is achieved, then that completes the testing process. Hardware development process is, say, cyclic in nature. You repeat the process to continue to develop better and better, better and better products. Checks and balances exist at each step, such as peer reviews, verification, validation, audits. Right? Importance is given to quality, objectives, cost, time, realities, those aspects. Of course, the decision making requires understanding technology changes, what technologies are changing. You are basically, let's say, building a hardware with a USB interface. You basically look at, what USB interfaces are available. Is USB 2.0, 3.0, USB on the go, and so many things that basically are the technology around USB itself. So you look at it basically. Are you taking advantage of the technology changes? Are you building a 3.0 version? Are they basically opting out to a lower standard, 2.0, and those kind of things? And component availability, basically again, we need to look at whether the components are available for a production. If you go into production, are they usually available? Are they going the end of the life period, end of support of that stuff like that? Basically, are all involved in the decision making in a hardware development. Supply chain, external factors. These are all basically involved in the hardware development process, design, decision making. Right? We'll talk about a little bit about the next topic is analog design and digital design. There's a lot to talk about it, but basically distinguishing between analog design and digital. And analog design is basically uses analog components, transistors or oscillators and all the analog components, discrete components, put them together into analog design. Right? Focuses on accuracy of signal voltage. In an analog design, you're dealing with a continuous voltage, basically starting from 0 to 5 volts or 10 volts or whatever it is. So the accuracy of the voltage is important. You need to focus on the accuracy of the voltage, but that whatever needs to be looked at it, such as let's say you are basically creating an amplifier using an instrument amplifier of something. Then you look at things like common mode rejection ratios, ground noise, and eliminate noise, and also the frequency responses. You also focus on the desired frequency responses. Depending on what circuit does, you would have to look at it. Are you allowing enough pass band for the particular circuit? If it is a filter design that you're doing, does it have low cutoff frequency, high side cutoff frequency? And these are the things that analog designs really focus on. And example of an analog design, basically a data acquisition system. A data acquisition system that basically acquires an analog signal from a field and then basically represents into a digital domain, converts into digital domain, displays and all. There's a lot to it than what I'm saying, but it is an in-depth subject itself, and we're basically talking about analog designs, distinguishing between the analog design and digital. Digital design focuses on prescribed digital interfaces, interfacing different digital sections with proper interfacing, interfacing ICs, and keeping the switching noise low. One of the challenges is keeping the switching noise low. You use different coupling capacitors, or, different techniques to reduce the switching noise low and all. Example includes network appliance, maybe some kind of appliance that is connected to the network. the appliance may be capturing data from the user interfaces or from the from the process that is taking place in the hardware box, and then sends it on over to a network, right? So these are the things. The digital design can go into high speed designs and all that, um, and throw in a lot of challenges in terms of signal integrity challenges that one need to handle and all. The analog design, basically, if you're going in high precision analog components, then you're basically looking at really high precision amplifiers and high precision components that basically uh, look at even low voltages, low currents, measuring low currents. Um, so they can be any bit challenging, either analog design or digital design. There are two different portions of it. If you are basically, oftentimes you would have a mixed signal design where basically you need to look at both the digital as well as the analog part. And most there is really these days with so much of computing power and automation and all that, lot of the analog designs basically include digital design also. They bring in the keep the analog portion low and then bringing it into a baseband processing or some kind of digital processing, and then do the processing there. For example, if you take a software-defined radio, it reduces the analog design to the extent of capturing at a very high speed the analog data, and then process everything in the digital domain. The modulations, the demodulations, filtering, and all kind of things, equalizations, everything is done in the digital domain. So we talk about, we're talking about a mix of things here, just to keep an understanding of the breadth and depth of the subject in that this course covers. Passive components, we're talking about passive components. Basically, resistors, capacitors, inductors are called passive components. Like said, resistors, ohms, capacitors, farads. If you've done basic physics or basic electronics degree, you understand what these are basically. A resistor is essentially is basically it, its response doesn't vary with the time. So it's basically if you your it's basically follows the Ohm's law, and basically whatever the voltage you apply, the current that goes through is basically linear, and that's how it functions. Whereas the capacitor and inductor, they don't function linearly. They basically have time varied response. Basically, if you apply DC across the capacitor, initially it works like a short, but after some time it basically charges fully and then works like an open circuit. Whereas the inductor is the other way around. Initially, when you connect it works like an open, and then it's basically charges it works like a short circuit, right? So these are the passive components. Typically, I mean, the passive components can be used to create filters, passive filters, low order filters, essentially. Right? These are some things that you may have studied in your engineering. They have time varied response, and their also frequency response also their frequency domain response will also be very different. This is an RC filter. Essentially, if you apply voltage here or a signal here, you get the output here. That would basically, if you are applying an AC voltage, it would follow frequency response like this. It would have a cutoff frequency, which is basically a low pass filter, passes all the low frequency signals and cuts off the high frequency. For a high frequency signal, the capacitor works like a short, and then it cuts off the voltage basically here. It doesn't allow the high frequency voltage to go here. The same thing can be created with a C here and then R here. That's an RC filter also, but that's basically a high pass filter that passes high frequency components and cuts off low frequency components. That's how basically it would work. So the cutoff frequency is typically 1 by 2 pi RC. That's the formula for this. That's the cutoff frequency. And one can use the RC and L and create a network of components and create a filter. And basically, you need to do an analysis of filter response to see how the filter is. Well, a simulation can actually do the response in you know, a spice model or something that we create and we do a simulation in hardware, and you get that. This is an LR filter, and it's basically again a low pass filter passing the low frequency. And on the other side, we look at it the time varying response. This is on the frequency domain. We are looking at how it is. And then if you look at in the frequency domain, if you are applying a square wave has infinitely many frequencies. Basically, it is has a DC component and then this high frequency component, and in between all the components also it has. So if you apply such a thing, the transient responses are very low frequencies of this square wave. It would basically be like this kind of response, medium frequencies like this at high frequencies like this. So if you look at this, this is basically a high pass filter. It passes the high frequency component. That's the edge is a high frequency right here. So there may be a rise time that is involved with this high frequency in this rising edge. That may not be instantaneous. Practical practical circuit components will not have a infinite frequency there. It would basically will be raised in a 1 nanoseconds, 10 nanoseconds, 100 nanoseconds, whatever the response time there may be. Right. So the lower the rise time, the higher the frequency is basically. So it passes because this is a high pass filter. See, it passes the high frequency component as is. The low frequency component is suppressed here basically. It's the low frequency component kind of tapered into multiple frequencies there basically. And that well at very high frequencies, the very high frequency this itself is basically very high frequency. So it clearly produces this kind of frequencies there. So that's what to expect from these kind of passive components, right? You can basically build on based on the passive components and something discrete components. Although the modern designs really don't focus so much on discrete component design, uh, but specific industries may require discrete component design, such as maybe some automotive industries still use discrete components to do a lot of uh, things like. And basically, how do you analyze the transient responses, the currents, the AC characteristics, based on basically Ohm's law that basically tells V equal to IR, and Kirchhoff's law. Kirchhoff's law basically, if you have a network, basically at any point, basically what Kirchhoff's law say, at any given point, all the currents going in and out of that junction is basically sum of those currents is zero. That's what. And if you take a loop of the in a circuit, the sum of the voltages in the loop basically voltage drops and voltage rises basically together will become zero. If you add them together, it's zero. So that's basically all DC analysis, basically transient response to time analysis. You'd also do the AC analysis basically by looking at the um, complex analysis that you do on the circuit cards. I mean, if it's at this introductory webinar, it's basically too much to go into the depth of it. But those are the passive components, and those are the characteristics and the phenomena that basically look at these passive components. Now, active components. What are active components? So basically, diodes, transistors, FETs, MOSFETs, op amps. These are basically all active components. Typically, like if we look at a diode, basically it's a two-terminal device that you all remember from your electronics basics. Basically, has an anode and cathode, and then it basically works a different way in the forward direction and the reverse direction. It basically conducts only in one direction. Essentially. It allows the current to flow through only in one direction, and the other direction it will stop the current to flow. Basically. For Zener diode, it's slightly an exception. We'll look at it, which where it basically goes beyond the breakdown voltage. The diodes have something called breakdown voltage. Beyond the breakdown voltage, it will not basically stop the conduction flow of current in the reverse direction. Also. There is a limitation to the reverse current. But that's what basically a diode is. A typical diode may have a drop voltage of 0.6 volts drop, but there are special diodes called Schottky diodes, which are basically special purpose diodes. They will have very low forward voltage drop, like 0.2 volts, 0.3 volts. And what are the other type of diodes? LEDs. We all know what is an LED is, basically. In the modern world, everybody knows what a light emitting diode is. Basically, when you pass a current through it, it basically glows. It gives the glow. Zener diode is another kind of diode. Basically, clamps the voltage to a fixed voltage. Photodiodes are basically the diodes that basically, when uh, light falls on the diode, it basically generates current. It basically does the reverse of LEDs. So these are the diodes, right? And the other active components, the most popular components are transistors and FETs, basically. Basically, these are can be used in basically linear region or a switch in non-linear region. Basically, analog electronics use transistors in linear region on the analog designs. Basically, they use them in linear design, in amplifiers, in with a certain gain and all that. Digital electronics use transistors and switching devices. Basically, transistor is used as switching device. Basically, in saturation and go to that, and then basically you apply uh, any voltage beyond the logic one level. It will basically operate one way. Logic zero level, you operate. You will never operate in the continuous region. 0.3, 0.4, 1 volt, 2 volt, 3 volts, etc. It's basically the voltage region is divided into logic low and logic high in a digital electronics. Whereas in an analog world, basically it is uses a continuum. Basically, if you are building an audio amplifier, it has to, every sample it has to properly amplify and all that. So in linear region, the transistor offers a gain. Basically, it offers a gain, gain of 2 or 3 or whatever it may be. If you apply an input voltage, the output voltage will be several times of that. And in switching, transistors work like a transistor works like an AND gate. If you have basically a couple of inputs connected through a resistor to the base of the resistor, the output will be NAND of the basically. Or if you have only one input, it works like a NOT gate. Basically, a transistor works like a NOT gate. And this is a transistor, and this is a FET. And there are special type of FETs called MOSFETs also that are basically a different semiconductor construction MOSFETs. But they all are used in these kind of circuits basically. Either amplifiers in a linear region operating for analog electronics, or basically the switching kind of mode, basically where they operate as a logic devices. And they all have NPN and PNP. In transistor has an NPN type of transistors, PNP transistors. NPN is most popular because they use it basically a common negative line. So the common negative line is used for both the input side and the output side. So the ground can be connected to this point, and this is a usual convention. And having a common line here, basically having a common supply voltage on both sides, is basically a little odd. It's not as common in circuits, whereas the NPN is common in circuit design. Now we talk about, so that's basically about the active components a little bit. I may be rushing through, but hopefully, if if you're not understanding concept, these are basics that one may have already gone through. You can feel free to interrupt me and ask a question rather than putting it hold to the uh, Q&A session. That way, I know you're following it. Now, there is a concept called voltage source and current source. A power supply or a voltage a source that sources voltage or current. Basically, there are two kind of sources: a voltage source and a current source. A voltage source basically sources a fixed voltage. Current sources a fixed current. What does that mean? A voltage source, if you apply any kind of load, let's say a 5 ohms load for a voltage source of, let's say 5 volts voltage source, if you connect a 5 ohm resistor, it basically sends a 1 amp current. If you apply a 10, if you connect a 10 ohm load, it supplies a zero point 0.5 amp current. That means its current is varying. It basically varies the current to suit the load, whatever the load is. So the load is typically measured in terms of amps there, basically for a voltage source. For a current source, it's measured in volt. It, irrespective of what is connected, whatever resistor, a simple load is a basically resistor, but the typical loads are basically quite different, and they're varying with temperatures. They're varying with different load conditions, different environmental conditions, and all that. So a current source basically, mm, uh, the current is a fixed current. Let's say you may have a 2 amp current source. The 2 amp current source, if you connect a 5 ohms, it will source 10 volts. Sorry, yeah, 10 volts. If you connect a 10 ohm resistor, it will source 20 volts. So it will build up the voltage irrespective of what the load is. And in order to ensure that the 2 amps current is continuously supplied. Right? Now, that's basically real it's not a real life scenario. In a real life, the power supplies are not ideal. In an ideal condition, irrespective of what the load you connect, basically the a current source will supply the same 2 amps current source current or whatever it is set to. An ideal voltage source has a zero series resistance. Typically, a voltage can be source can be voltage source can be seen as a containing a series resistor in an ideal source conditions. And the voltage across this, basically, if you are increasing the current, basically that means if it's drawing more and more current, some voltage will be dropped here. So practical source would look like this. If the current is increasing, then the voltage across the AB that it is supposed to source, it's supposed to source 5 volts, that keeps coming down. It may come down to 4.8, 4.7, 4.6, whatever, if you keep increasing the source. So a practical source would will have some kind of limit typically. If you supply beyond that limit, it would basically drastically drop down, right? It may even have a curve like, you know, till certain point it will be flat, and after that it will fall drastically to voltage. So a practical voltage source will have a V versus I curve that is not linear, not straight line like this. Same thing with current source, except that the current source is seen as a practical a parallel resistor in parallel with the current source. That means if the voltage is basically being drawn, more and more voltage is drawn, then a lot of current that goes through the parallel resistor of the current source. That way, as the voltage is increasing, the current will drop in kind of a ideal current source. Yeah, practical sources are not ideal and have definitely equivalent resistance in series or parallel, depending on the sourcing voltage or current. So that's something to expect from practical sources. That basically throws the design challenges. So ensuring what is the current budgeting, or the what is the voltage, the operating voltage in which it would operate, and all. Those parameters need to be considered in designing the circuits. So we talk about amplifiers. Amplifiers are basically designed using transistors and FETs, we said. So this is a typical transistor amplifier. It's a single transistor. We said a single transistor, when it is operated in the linear region, it acts as an amplifier. Basically, you apply a small signal, it basically amplifies it to a large signal. Basically, you apply a voltage V here, depending on the transfer characteristic of the transistor, it will offer a gain. The output will be multiplied by n times the input voltage, the voltage that is applied here, right? So the bias that you apply, it takes that. If you apply a sinusoidal, it basically the sinusoidal will be here, maybe from 0 to 1 volt range you apply. Here you will get it 0 to 5 volts. Basically, transistors are used for voltage gain. They typically as a voltage gain. The FET is typically as a current gain. Works like a current gain circuit. Of course, if you properly connect these transistors and do the design, you can get either current design gain or a voltage gain. An amplifier can be a single stage or a two stage. Typically, this is a single stage. That means you have only one transistor there. A two stage, this is, if you look at it, the same transistor is basically connected here. This is a two stage amplifier. So what is the advantage of two stage amplifier? It offers higher gain. Basically, you may get a gain of 2 volts, then two times. That may not be enough, and then basically connect two of them, you get a gain of 4. 2 into 2 multiplied, a gain of 4. To get a higher gain, you use multi-stage amplifiers, right? The next thing is op amps. Op amps are typically, basically you get them in IC form, basically not as transistors. Okay? Op amps are basically differential amplifiers. It's something like this. If you basically look at it inside the IC, it would have some kind of circuit like this. It will have a V input and V1 input, a differential input. Basically, you're offering a differential input is offered. That means a voltage is a drop across two pins, right? V1 and V2. So you apply a voltage across these two pins, and the output will be coming across these two pins. So here is the symbol, the V plus V minus, and then V out is basically with respect to ground, basically. And typically, op amplifiers have two power supply rails, Vs plus and Vs minus. That's it. You can also operate them as one side as ground and one side. They're basically all uh, op amplifier. There are many ways op amps can be connected and all that. What are the main advantages of amplifiers? Is basically they offer very high input impedance. That means they don't load the input signal. Let's say if you have a signal here, if you're loading the input signal, the characteristics change. What the it is loading the other one. It basically have a high input impedance. That means very low current that it would expect the input device to send. The input device may not be capable of sending high current. If it is sending a signal, it may basically only offering milliamps or even less than milliamps. So the op amp typically takes only micro amps of current. It doesn't take milliamps of current. So it doesn't really load that a great deal, but then you get the signal here properly, and then you can drive a much more current on the output. It has a basically low output impedance. That means the output is basically you can drive a high current to the output, and then if you are basically driving an amplifier, a motor or something, where this characteristics is basically driving the motor, then you can actually use an op amplifier circuit to drive the motors, so that the high current is basically driven into the motors. They often offer a high gain. Basically, op amps offer very high gain compared to regular amplifiers. and then they also have low input offset voltage. That means if you apply 0 volts across this, ideal op amplifier is basically a myth, right? Basically, you may not have an ideal op amplifier. If you in ideal op amplifier, if you apply 0 voltage difference, same terminal you connect between both these inputs, the V out should be 0. That means it should be ground level. But really, a practical amplifier basically will get some voltage across here. It will not be ideal 0. So that is basically called low input offset voltage. So it basically there is a very low input offset voltage compared to the ground level. And there are other things like common mode rejection ratio. Those are all basically good in op amplifiers. More specifically, instrument op amplifiers are yet another class of op amplifiers which offer very high common mode rejection ratio. They also offer wide passband, basically. The AC signals that you send in basically have wide frequency range. Of course, you will still, if you're designing a filter, you have to carefully design to have low enough cutoff frequency and high enough cutoff frequencies and stuff. Op amplifiers can be used in many applications. Here is an inverting op amplifier, where you are applying an input and the output is basically the gain is minus RF by Rn, and the output would be typically negative side. Basically, if you apply positive voltage here, you get a negative voltage here. This is a non-inverting. Basically, if you apply a positive voltage, you will get a positive voltage. But the gain here is 1 plus RF by Ra. So that is the gain. By adjusting the resistors, you can actually get the desired gain that you want in these outputs. That is used as a amplifier. They can be used as filters also. Here is a low pass filter giving a transfer characteristic like this. Here is a op amp high pass filter giving a transfer characteristics like this. So the op amplifiers compared to the RC filters, the op amplifiers much steeper cutoff frequencies, much steeper. They will give a higher order filtering characteristics. Basically, this slope will be steep in the op amplifiers. Right. So those are some of the things, but we didn't really get into the design considerations of op amplifiers and all that. There is so much depth into those that one need to go through. We'll skim through to the logic gates. There are many kind of logic gates that you basically come across: NOT gates, NAND gates, NOR gates, OR gates, and XOR and XNOR gates. They all have truth tables. Basically, NOT gate, if you apply input 0, the truth table is 1. If you apply 0, it will basically output will be 1. If you apply 1, output will be 0. And an OR gate, basically, if both inputs are 0, if either one of the inputs is 1, it will be output will be 1. Both are 0, then it's definitely 0. NAND gate is slightly different. Both of them need to be 1 in order for it to be 1. That's an AND gate. Here is an AND gate. An AND gate is basically opposite of AND gate. An AND gate, both the inputs need to be 1 in order it to be 1. And if any of them is 0, the output will be 0 for an AND gate. For an AND gate, it is a complement of that. It's any of them is 0, it will be 1. Here is an XOR gate. XOR gate is another different kind of gate where basically if you have both the inputs are same, identical, the output will be 0. The inputs are 0, 1, 1, 0 like that. Basically, you will get 1 as an output. That's an XOR gate. So these are the logic gates, and here are some ICs. Basically, 7400 is a quad 2 input NAND gate. That means there are basically 4 NAND gates in this IC. Between pin 1, 2, and 3, A1 and B1 are the inputs of the first NAND gate. Y1 is the output of the first NAND gate. A2, B2, and Y2 is another NAND gate. Similarly, A3, B3 are inputs to the output of the Y3 of this third NAND gate. So there are 4 NAND gates here. Here is a quad 2 input NOR gate, this 7402 series IC that has basically four NOR gates, one A, one B, and one Y, 2A, 2B, 2Y, 3A, 3B, 3Y, 4A, 4B, 4Y. That way, and then here is an X NOT gate, so six basically NOT gates are there. One A is the input, one Y is out. 2A is input, 2Y is out. So you can basically, this includes six NOT gates that you can use in your circuit design for the NOT gates. And when you're using these, basically the 74 series ICs, you may come across 74LS, 74HC, 74HCT series. What are those? Basically, the logic, when you are talking about digital design, basically you may have a TTL design or a CMOS design. Of course, these days, most of the designs have become CMOS designs. Very rarely people use TTL designs. Maybe some industries may still include TTL design because of their legacy. There may be designs of 20, 30-year-old designs. If somebody is basically building a ship, the ship basically will last for 20, 30 years. Or similarly, somebody is building aircraft, probably are changing much faster. But the shipbuilding industry, they only build two or three ships, and then a lot of legacy components typically in the shipbuilding industry. So they may use still TTL logic. So 74LS is TTL logic, 74HC is CMOS logic. 74HCT is a like mixed variant hybrid logic. Basically, if you use 74HCT, you can mix TTL and CMOS ICs together. It will work with both CMOS ICs as well as TTL. So depending on what you are doing, you basically properly select those. If your design is all in 3.2 volts, 1.8, 1.2, the CMOS logics and all that, or the LVTTL and all the 74HC series is what you use. So you need to be sure of what kind of ICs you use. And then another digital circuit element is called flip-flop. There are many kind of flip-flops, but we're looking at something called D-type flip-flop, which is actually built on top of a SR flip-flop. This is this part here is an SR flip-flop. This is S and R, and it is gated through a clock in a D-type flip-flop. A D-type flip-flop, a clock is applied, and whatever input you take, it is complement of it you take to the R input here, R input, and Q and Q bar. So it basically, I didn't give the truth table here, but essentially whatever you apply here, one, at the clock edge, basically when the clock is edge at the clock edge, that logic is basically sent to the queue, basically, and it retains that in the queue, basically. If you apply logic 1 and you apply a clock, the 1 basically goes to it. If you apply a 0, the 0 will be transferred to here, and the complement of that is present in the queue. So this is typically called a D-type flip-flop. This can be used in a memory element. Basically, what you are applying here, that is transferred into this, and even if you don't apply clock or anything, the output will be retained basically, right? So that is, or even if you're applying a clock, whatever is there here, that goes into the type flip-flop. Typically, a flip-flop that you may get in the industry, the 74 series and other, it may have additional uh, inputs also. It may have a update input that will basically update, or reset input that will clear the Q signal. It will have additional inputs. And a D-type flip-flop can also be used as a delay element. That is why it is called a D-type flip-flop. Essentially, it will delay it by one clock cycle. If you are applying a bit stream here, the bit stream here, if you see, versus the bit stream here, there will be one clock difference basically. Whatever you are applying, if you are applying multiple clock difference, multiple D-type flip-flops and sending a bit stream, this output will be one clock different. The cascaded next D flip-flop will have one clock after it will produce the bit and etc. That's basically why it is called a D type. So this is a flip-flop is basically essentially formed out of these NAND gates by giving a feedback, this kind of feedback, crisscross feedbacks, right? Um, the flip-flops are basically building element for counters. What is a counter? Counter is basically built up from flip flops. The counter, for example, here is a 4-bit counter symbol. Here 74LS69 IC it is. It is a 4-bit binary counter. What it basically does is it counts from 000 to 111. With every clock cycle, it will basically increment this binary fashion: 0000001, 0010, 0011, 0100, etc. It basically increments in a binary fashion. So here, if you say these are the 4 outputs, the counter outputs, a clock input here, and then it also has a clear input. When you set this to 1 logic, the output will be clear to 00. They all will be clear to 0. That's basically a counter. Counters have a clear control signal, like we see here. If you this IC 74LS920 74LS69 has 2 counters. This is 1 counter and this is counter. 2 counters are built into it. 74LS68 is another counter, which is actually BCD counter. It actually counts from 0000 to binary coded decimal, right? So essentially to 9. So it will go up to 9. After the 9, it will again reset to 0, basically. So that's how the BCD counter basically works. So that's a little bit about the counters. I'm not sure how are we running on the time. Yeah, we're almost 1 hour. I think another 20 minutes or so we should be done. 10-15 minutes, I think we should be done. Next thing that we're looking at is power supply design. Basically, power supplies are two kinds. Basically, linear regulated power supply and SMPS, switched mode power supplies. Basically, there are two kind of power supplies that you come across. Basically, these power supplies basically generate a small DC voltage from a main supply, AC main supply, 230 volts or 110 volts. Basically, the difference between these two is basically a linear regulated power supply, which uses a bulky transformer and typically not efficient. It is only 40%, 50% efficient. That means if you are applying a power, let's say 100-watt power, it will only deliver to the output load only 40, 50 watts of power. Remaining 40, 50 watts would be dissipated in the power supply itself as a heat, basically. But the thing is, they are very simpler designs, very simple to design, and not much complications and design techniques to be used, design analysis to be done. SMPS is the other side. It basically uses high frequency switching and DC-DC conversion. So its efficiency are basically 90%, and designs are more involved. You need to understand more. You will have a controller IC that will basically control the SMPS, the conversion. Power supply design is basically a subject by itself, known as power electronics, that involves basically a lot of things in the power, basically ensuring the power supply characteristics, such as depending on whether you are doing an AC to DC conversion, the ripples and the harmonics, those kind of things are basically involved in that. And one can build a power supply from discrete components or use integrated solutions from companies like Texas Instruments. Right? One may build a very discrete way using resistors and capacitors and all that, and discrete components, like discrete components for our voltage and voltage protections and all. Or one may basically what you call use an integrated IC from Texas Instruments, reduce the component count and build that way also. Again, one may build a power supply that generates a fixed voltage from mains, like 230 volts and 110 volts. Or one may build a power supply circuit that generates different power supply rails, such as 1.2 volts, 1.8, 3.2 volts. Require the chips basically on the PCB. Typically, it's generated from a 9 volts, 15 volts, or a 24 volts industry power supply input. So here basically the difference between these two is basically whether you are supplying AC mains or an industrial supply voltage, basically, right? Either way, you will have to supply some voltage for the power supply. It will not supply the power supply out of nothing. You have to uh, connect some kind of power supply, power, and then that is what it generates. So it may be a 230 volts or 110 volts means, or maybe industrial volt, where the industrial voltage is given from either a battery bank or maybe some other mechanism. That's basically what is generated. So these are the design here is different and the designs here are different. So the power supply design basically focuses on all these. And power supply design need to consider voltage for power voltage protection, under voltage protection, regular protection, short circuit protection, regulation. These are all the things for the primary supply, the power supplies, basically that operate from 110 volts and 230 volts. PCB design should consider power budgeting, a process that verifies basically enough current can be supplied by the power supply for all load conditions, different conditions that are the loads may run at. The microcontroller may run at different frequencies. For irrespective of whatever frequency it runs, the power supply need to power supply the current, necessary current. EMI, EMC considerations. That is another thing. Basically, whether it is generating a humming noise, so that other nearby electronics will catch that noise and also get affected. So reducing, suppressing that noise, ground noise and the EMI noise, and the external noise coming into the power supply, into the circuit through the power supply. Those are the considerations that one will get, right? So that's a little bit about power supply. We're not really going into the design of it. Essentially, the course will basically go into the design sessions for the power supply and all that. Just a gamut of things that are there in the power supply is what we are. Now we look at microcontrollers. Basically, microcontroller is a central processing element that manages the entire hardware, runs the software. It is the brain of the of any hardware design, right? So there are 20 to 30 semiconductor manufacturers that make microcontrollers. There are all kind of microcontroller designs, right? Some of the popular are TAL, Texas Instruments, ST Microelectronics, Acme, Freescale, Landmark Devices, NXP, Marvell, Renesas. These are all the names that commonly bring in the culture of the designers people use these. But there are many companies like this that really make microcontrollers. So choosing a microcontroller is the key to success. One need to pay attention to cost of the processor, processing power, many parameters that are basically going to the microcontroller selection. Microcontrollers, basically microcontroller these days are more like in a system on chip. They have inbuilt circuitry to handle different kind of purpose. They have all kind of subcontrollers within the microcontroller that can handle the peripherals designs, like an I2C or an SPI or basically Ethernet, etc. So they have all the control additional circuitry built around the microcontroller that can handle the peripherals. One need to look at it. And another important thing is these days more and more microcontrollers are becoming built on ARM cores. Of course, there are still some legacy cores are basically proprietary cores from manufacturers that are available. But by far, more than 70% of the microcontrollers are on cores. If you take mobile industry per se, 90, probably 100% of them are on cores, basically. More than 90%, I'm very sure, are very sure, I mean, confident that 100% of the mobile units are basically uh, built on ARM cores. ARM microcontrollers are basically now have two series, M series and A series. One need to really thoroughly study the ARM cores to see what are the differences. There is Cortex series, Cortex M and Cortex A series. Cortex M series, M0, M1, M2, M3, and even M7, and those are the things. There are basically low-end applications. The Cortex A series are like dual cores and high-end applications basically. A series is for the high-end applications. Every month now, if you take a manufacturer, every manufacturer has multiple brands of microcontrollers. In each brand, there are a series of microcontrollers to choose from. I take one example here, basically ST Microelectronics. ST Microelectronics has basically branded their microcontrollers. They've said STM32 series, MP series, STM32 mainline series, and then automotive series, and basically STM8 MCUs. These are all 8-bit microcontrollers, um, basically from STM. They're not ARM cores. These are basically ARM cores. These are all ARM cores. Automotive, I'm not sure whether ARM cores. This is the main series. So in this main series, they have so many of these processors in the STM32G0, STM32F0, F1, etc. They call this mainstream ultra low power high performance wire. That's how they are branding it. It's there is typically not much of a, logic behind these branding. They basically brand it in their own way, right? But if you go a little bit more on the STM32 MCUs, these are MPUs and these are MCUs. Look at the MCUs here. Basically, they're telling about the frequency at which they operate. This is basically STM32L0 is operating in 32 megahertz. This is operating 32. Here 110 megahertz, 120 megahertz. This is all ultra low power, right? 120. So they're basically low power means low frequency also. With the frequency of the processor increasing, the power that it consumes also would increase. That's typically what. But it's a low power design, basically like 120 power megahertz it operates low power. Here is a mainstream that basically has 170, 72, 48 megahertz, 64 megahertz, all kind of branding here. Again, between these processors, if you actually drill down a little bit more on the website and try and look at it, they may have different kind of peripherals support. It may, something, for example, 170 megahertz may support Ethernet, and the 72 megahertz may not support Ethernet. Those are the variations. The peripherals will be there, variations will be there. Here is, they call them high performance. High performance is not gigahertz, but basically 240 megahertz, 480 megahertz. Within that series, they are basically high performance. That's how it is. The branding is basically, that's how they have branded it. But just to see, if you look at the more specifics, the details, it's a 480 megahertz processor, 240 megahertz. There is a 120 megahertz. The minimum in this series is 120 megahertz series processor. So this is how we go about it. And what do you basically look at it when you're selecting a processor? Look at the compression power, the bus size, 16-bit or 8-bit, right? Of course, more and more it is becoming a 32-bit nowadays. Everybody is, the software becomes simple, uniform, and basically portable and all that. And at the same cost, low cost, ARM processors are coming at low cost. You can get $2 processors, so not very expensive. Of course, if your application really only very cost sensitive, then only people are using 8-bit. Otherwise, a lot of the 8-bit, 16-bit old legacy designs have been converted to 32-bit designs, or most often 32-bit designs are used. Other special purpose requirement, digital signal processing, network processing, graphics processing, based on the things processor selection will be there. And the process will have on-chip memory. How much on-chip memory you need, that's one consideration. Choice of the peripherals, whether it has USB, Ethernet, etc. That's what we look at. Power consumption, cost of that, environmental requirements. That is, say if your uh, processor need to work at 100 degrees centigrade, then you need to basically look at those aspects of it, environment conditions you need to consider. And of course, your familiarity is also basically the designer may be more familiar with STMicro, so he would basically choose STMicro as opposed to TA. So these are all the uh, uh, considerations one look at it. Package, what kind of package, PGA package and LPF package, those packages that are available. People may opt for LPF packages because of its production easiness and all that, right? And different other considerations such as longevity, how long the processor may be supported in the market. Will it is it nearing the end of the line? Have they given a not to use for new designs notification, or have they given any specific indications that it will be supported for 10 years, 15 years? Some manufacturers basically do that. So those are the things. A typical microcontroller, here is a microcontroller, STM32G431 RB microcontroller, basically, that has all these peripherals in it. Basically, it has three SPAs, three I2C, four UART, right? I square S interface. It has a CAN interface. It has USB full speed and including a file on that. It also has accelerators such as the trigonometric accelerators, filtering accelerators, other basically uh, uh, um, encryption accelerators and stuff like that. It has sensors, basically analog sensors, temperature sensor, built-in analog temperature. It has sensor. It has a 12-bit ADC, basically mixed signal here. 12-bit ADC built into it, and then these are all the timers that are available in there. And then it has all these 22 kilobytes of SRAM and 120 kilobytes of flash memory inbuilt into it. These are all. It has a floating point unit. That means you can easily do floating point operations and stuff like that. And it is built on a Cortex M4 microcontroller. So which essentially means it has Cortex M4 will basically have a memory protection. Right? So that's how basically one look at the microcontrollers. There is a lot to microcontrollers. I mean, it cannot be covered in one session. Basically, um, these are all the peripherals the microcontrollers support: RS-232, 485 legacy interfaces, LCD, keypad, SRAM, flash, wireless interfaces, sensor interfaces like high-speed CSP interfaces, USB interface, Ethernet, these kind of interfaces that are peripherals that are available. Here is a list of the peripherals: SRAM, flash, SPI, I2C. SDIO is basically an interface for interfacing SD cards. MMC is MMC cards uses another interface MMC. UART is for the serial ports and all that. RMIA, MIA, GMIA are for the Ethernet kind of interfaces, depending 10 gigabit or 100 gigabit Ethernet or a gigabit and 10 megabits or 100 Mbps or 1 gigabit Ethernet, depending on the interface. Of course, USB and interface, GPIO, general purpose IOs, basically. The digitals that come out of the controller, RTCs, timers, CAN bus, ADC, PUC, these are all the peripherals that are supported by microcontrollers, right? Each interface need to be studied, given enough time to study. One session may be needed for each one of these interfaces to study and understand what that interface, how to interface that, what are the challenges with the interface. Now we look at some communication mechanism. What is communication mechanism? The communication mechanism can be between a chip and another chip. It may be an inter-chip communication or communication from a board to another peripheral, or it may be a communication between a board and module, a communication between a board and WAN. Right? For example, inter-chip communication is like I2C, SPI. They are basically between chips, between one chip and another chip communication. Communication from a board to another peripheral is basically either RS-232, RS-485, or a VGA, or basically HDMI. These are with a peripheral basically. And between boards and modules, basically again you RS-232, 480, RS-232, 485, or even Ethernet, right? Between the board and WAN, basically again your Ethernet is basically WAN connectivity and all the WAN connectivity. So these are all the communications. They're all communications. There are so many concepts involved in the communications that one need to understand in order to be able to do a good hardware design. One need to understand synchronous versus asynchronous communication. One need to understand what basically involves in synchronous communication. A clock is usually involved in the synchronous communication. In asynchronous communication, there is no concept of clock. It is basically inherent in the bit stream itself. One basically recovered from the bit stream a clock internally in the IC itself. So it doesn't deal with the clock really asynchronous communication. One need to look at CRC, the chips basically, or the ICs basically do CRC check, or the CRC check, cyclic redundancy check, to ensure error is, coding is done. Error management is basically detect errors and all that. If there is an error in the communication. Similarly, you may have a preamble and postamble, that is to ensure a proper packet format, and it may have its own kind of packet format. It changes from communication mechanism to communication mechanism. There may be sync bits and address bits and all that. So every communication mechanism that we are looking at ISKC can, or basically, your basically these things change. And in every communication, there may be a master and a slave. There may be multi-master and multi-drop communication, where the masters and slaves, they all get connected to a couple of wires and basically communicate across those two wires. So they have to do something called arbitration, ensuring who is basically the owner of the every transaction of the data that basically happens. The transaction need to detect who is basically sending the data, who is owning the transaction, the master, and who is the slave that is basically responding to that transaction by sending the reply to that. So these are all concepts. There may be, if you're looking at Ethernet and USB, these kind of things, these 7 layers of ISO. I'm not sure if you're familiar with it, but basically it will have 7 layers. Basically, a lot of the layers are basically software layers. The top 5 layers are software layers. The bottom two layers are basically hardware layers. For example, 5, they all Ethernet 5 is basically a physical layer, stands for physical layer. Link layer is a MAC layer that is typically built into the microcontroller. Physical layer is a separate chip on the board, right? These are the things that you will study in Ethernet in depth when you are basically designing in Ethernet, right? Similarly, a signal may be a raw signal or a modulated signal. It may be wired or wireless, etc. These are all the different things that happens in the communications. Now we talk about switch gears and we talk about what is a PCB. I mean, all of even at eighth grader today, these days in the modern times, eighth grader understands what is a PCB. Every one of you have seen a PCB, what a PCB is like, most likely. And a PCB is basically consists of multiple layers of printed circuit. Basically, the circuit is printed on a plastic, right? And they are laminated basically together like this. Basically, this is a PCB with laminated, and there is these copper connections between these laminates. If you look at it here, there is a ground connection into this layer, and here, if you this is called a via. Basically, a via is connecting one layer into another layer here into the ground layer. Here is a VCC power supply connection into this layer. Typically, layout when it is generated, it will basically it will have something called folder mask, silk screen, and layers, something, etc. And then here is basically this is called substrate, the prepared copper. This is the copper. Basically, what you see is it is typically added onto this by etching process. Right. This we study in depth basically what a PCB is in one of the sessions basically, but that's basically PCB. It helps in converting whatever is given as captured in the schematic capture into a PCB like this, that connecting all the components and all. There are many type of PCBs basically, and PCB when you actually give it to production, you may basically ask the fabricator to create a FR1 or FR2, FR4, FR5, FR3. These are all the type of PCBs, the thickness and the type of the material that is used in the PCB that will make whether it is a per 4 or per 5 type of glass epoxy that you use. Each one of them has its own characteristics, and people use them differently. There are flame resistant if you are basically creating fire alarm products and all that. You may have to stick to the standards like UL94 and all that, right? Typically, again, there are metal clad PCBs. If you are creating LED lighting and all that, they use basically metal clad PCBs. One of the layers will be a metal, full blown metal that basically serves the purpose of dissipating the extra heat that is generated in the PCB to be dissipated into the external chassis and all. So metal clad PCBs are typically you find them in LED lighting. The LED lighting are typically generate a lot of heat because there is so much of light that they generate. Again, you may have a rigid PCBs or a flexible PCBs. So you would, depending on what your industry, what kind of application, you would basically make those kind of PCBs. Flex PCBs also are popular in the industries. If you look at basically a layout, this is the layout. If you look at it, the green is basically called solder mask. That means that's where the solder is basically applied to attach a component. Here is a component basically. This is a 14-pin component connect is here. These green ones. So these are the solder mask for the 14-pin IC. Here is basically a display, LCD display or something. That's basically the solder mask. Here is another IC here. Basically, the solder pads there. So typically green is solder mask, and then blue is basically the top layer. Blue is the top layer of the IC, and the red is the bottom layer in this. This is the basically two-layer PCB. This is the bottom layer, and white is basically typically silk screen. Silk screen is basically where information about the components or whatever information that is needed is printed on the PCB basically. Typically in a white screen. This is the silk screen. C2 capacitor 2 and 10 microfarads is what it is. 100 nanofarads is given here for this capacitor, etc. Those are the things basically. And PCB may have through-hole components and SMD components. They basically people use both those components depending on the industry. They may change and all that. Depending on the size of the board, they may change. Even for smaller size of boards, you may use SMD components. SMD components can basically go really, really small and all. Now, the design itself, the schematic capture, the design of itself will basically go through basically processor peripheral selection after the hardware requirement document is come up. You would basically do the hardware design analysis during which you will identify the peripherals, you identify processor, you identify the peripheral chip selection, right? You study the interfaces and do the interface design and also do the power supply design and then the power supply components, both primary power supply, secondary power supplies, and all that you look at it. The boot design basically, even though it's not the major design, it's a critical part of it. How the processor will boot, where will it start the code from, where will it acquire the code from, and all that. JTAG design is basically for downloading the code into the microcontroller and all that. We'll also look at layout precautions, how the layout need to be done and all that. And once this design flow happens, your design is complete, you offload it to a layout designer, a layout basically engineer. The layout engineer will import the schematic capture, the logical design into it and basically auto-generate a layout or basically manually adjust the routes so that it is basically more efficient and all that. So that is basically a layout design. Now, what are the career options for people that do go through this kind of course? For example, for example, today, like you have firmware design, firmware in expertise of 10 years of firmware experience, and wanting to learn hardware. So basically options, basically one that goes through this course and basically gains this kind of knowledge, they basically can obtain jobs in semiconductor manufacturers or IoT and device manufacturers or contract manufacturing service companies or ODMs, uh, uh, outsourced design manufacturers, or engineering and IT service companies like Accenture, Wipros, and all that, or semiconductor manufacturer like analog devices, Texas Instruments, stuff like that, IoT and device manufacturers, right? These are the kind of companies that one can actually expect career in jobs in companies. And career choices, basically, you can get into R&D, product engineering, and all that, or you can get into applications, or you can get into hardware testing or verification, production also, basically, when you gain this kind of knowledge, right? Of course, although we are basically, this course is about design, basically, but even in the production you may have to have a design knowledge so that you be able to perform the job perfectly. So, what kind of design roles will be there? Basically, application engineers, design verification engineers. Application engineers are basically, in a semiconductor company, you may have application engineers. They're building on the microcontroller or whatever the chips that they may build, the manufacturer offers. You build applications around those chips, basically. You build boards around those chips. Design verification engineers basically verify them. Again, similar like application engineers, but they verify them by building on the board and creating a board and verify all the functionality and the parameters, performances, and stuff like that. The application is more focused on the functionality. The design verification engineers focus on the performance and all. Board level engineers, basically, some companies may call board level engineers. That means IoT and device manufacturers, they typically may call board level engineers. They don't call design verification engineers. And one can become a system manager, both looking at hardware design and software design and overall management of it. And board architects, involved in the complete board design. There may be multiple designers designing each of the sections and the performance at that and all that. So some boards may be really complicated. 1 GHz boards with DDR kind of memories and stuff like that. So the career, those are the career choices, basically. Uh, and the jobs are available in telecom, medical, transportation, automotive, pretty much every industry that you can think of. Have hardware design and development. Wherever the hardware design and development is there, you can basically do it. The ODM, it may be after development and manufacture, developing products for other major brands. There may be, if you basically think of Tata may have telecom products. The telecom products may not be made by Tata itself, but somebody else designing and manufacturing for them. Tata branch for them, branch those. So that is possibility. So there are ODMs like that basically um, create these kind of products. So those are the, and one can basically also get into hardware testing. Hardware testing also involves understanding of the design, thorough understanding. You may be a very good debugger or a very good tester. You may like testing more than uh, product engineering. So it is all a choice of individual and their core competencies. And these are the different career possibilities that are there. And about this course, certification training, basically again, repeating that, it basically focuses in-depth knowledge of electronic fundamentals like microcontrollers, the interfaces, CAD systems, and all that, the industrial applications and all that. This webinar is basically only touches the surface of it, but the students, basically participants, will then learn in-depth electronics, the circuit design, simulation with PCB designs, and all. These are the possibilities. It also covers a project if the student, if the participant is actively doing the hands-on, they can actually do a real-time project also in this course. With that, I'm done with my presentation. We've taken up quite a bit of time. I'll open the floor for questions and answers.
Hello.
Yeah.
Hello.
Yes. Hi.
Sir, can you provide the recording of this lecture?
Yeah. So whomever you are contacting with, basically our admin team will, our marketing team will basically provide it to you. You can ask them when you talk to them next. You can ask them for the recording of the demo.
And also I ask one question.
Yeah.
Hello. I
Yeah.
need
Please.
some deep depth knowledge of power supply design.
Okay.
Uh,
And also, are you also interested in microcontroller design and all that?
yes, yes.
Or you're interested only in power supply design? Just trying to understand.
But can you share me in mail about this course? What is the cost and what other things are there?
Yeah, they will be shared with you. Yes.
Okay, okay, sir. Thank you. And very nice
Hello,
session, sir. Ah,
Thank you. Yeah. Thank you.
ah.
hello.
Yes, sir. Hi. Yeah, Mayank.
Is there any
Yeah, please
feed?
go ahead.
Is there any feedback link?
Yeah, if you can actually leave feedback, that will be great with the marketing team. If you can leave a feedback, they'll probably link. I don't have a feedback link given here. Yeah, there you can send the feedback here.
Sir, Snehashi here. Okay, the first thing is like, I hope all the sessions will be accompanied with the practical session, right? Whenever you will be taking the regular session, at that time all the session will be accompanied with the hands-on practical. And the second
Yeah,
question is, in case we have to do the hands-on practical because this is the hardware design. So, okay, apart from the simulator, I believe that there will be some CAD tool by which you will be doing some kind of simulation. But apart from the simulation, if you have to do the hands-on also using the active elements, passive elements, and all sort of things. So at that time, will be there any kits provided from the center, or how it is?
yeah. See, we focus on the here basically hands-on is basically focused mostly on the schematic capture. One should basically be able to capture the schematics properly than the rest of the things. We don't do basically the course will involve a lot on the interfaces, basically I2C, SPA and all that, peripherals and all that. Right? The discrete design days are gone basically. People don't use a lot of, basically we want to be in tune with current designs, not so much of do a discrete design. Discrete design is elaborate. Lot of ICs basically have the design thoroughly painstaking. They do the design and put it into a VLS and use those ICs. So the design is basically more at the IC level, and basically selecting the component selection, the ICs, all that is given, and the hands-on, for a hands-on, one need to have basically ARCAD or a Altium or one of these tools that they need to have basically. And we basically run through the schematics, and one has to spend additional time in addition to the session, the presentation session, additional 1 hour every day. The session may take 1 hour to 1 hour 15 minutes, and one need to spend another additional 1 hour. Whatever is covered in the session, they have to manually draw it on the schematics, right? It's not, the hands-on is not overseen, but you expect homework be done by the hands-on, and cover that in the next session. Basically, we review that. Basically, you submit that hands-on session and then a review. That way, basically, the 25 hours of session will basically cover a lot of the subject. That's why we are able to cover subject. So the hands-on is more about the schematic capture. We don't do the discrete component analysis and dissemination and all that, because that is really meaningless. what happens in industry, even if one do the discrete analysis, basically if you're working for a semiconductor company, that will basically be captured into a VLSI basically. So that's the analog design, and that's basically only a small part. Power supply design is there. There are 3 sessions on the power supply design. That is the depth at which cover. But the peripherals are many. There are almost 15, 20 peripherals that are listed in the course. And those are all covered basically in the course. Because hardware design is an elaborated subject with so much of that, so much of breadth that need to be covered. Because of that, basically, we cover. We don't do the discrete design like resistor, putting the resistors, capacitors, and all. We focus on IC level methodology.
Okay.
Does it answer your questions, Nash?
Yeah, I understood. So basically, you mean to say like nowadays actually the discrete level hardware design is not happening anymore. So almost all kind of like say for even for the power control also we use the different kind of ICs. But eventually like to connect between the peripherals, different peripherals and the interfaces, anyway we require some kind of passive elements or the active elements. And so that level of hands-on we'll do using the schematic tool. Am I correct or?
Yeah. So this course is basically curriculum link is there. I think somewhere. We look at it. Yeah, it focuses. We would basically limited discrete components will be used. We would do that. I mean, if a pull-up resistor need to be connected, what value of the resistor need to be connected, that level of depth will be covered. Yeah.
Okay, and say for example, some Smith trigger is required, and all these things will be covered, right? Say in any smoothing kind of things, a Smith trigger is required or anything like that, you will be covering.
Yeah, very little focus on, I would say, very little focus on analog design. A lot of focus, 80% is basically digital design, 20% is analog design. So the Smith triggers and all that may not be covered, so to say. Anybody else? Any questions? Okay, one more time. Anybody has any questions? Not basically we'll cover. Call it close of the day. We'll close this session. Okay, thank you everyone for participating.